All right, good. So we learned about Gaussian elimination. Now, just a comment. If you look at the literature, then sometimes you see a little different description of it. They describe it by a forward and a backward step, but it is basically the same. They just do it in a different order. In a forward step, they create a zero matrix in the lower triangle here, and then they work their way up to normalize those values in the diagonal, so we get a 1 value here everywhere, which is leads to the same result and is basically applying the same permitted rules that we had. It's just doing them in a slightly different way. So I just wanted to note that, because if you look it up in the literature, sometimes you see it that way, and if you don't know it, it can be confusing. So it's very often, if you look things up in the literature, it's a little different, but it actually is, like I said at the beginning, it's I think it's very helpful to also look at other sources, and then if they explain it a little bit different, then to see how it compares to how we did it here. And then sometimes if you see they describe it from a different perspective, it helps you a lot in understanding it better. Like I said, for this time, the chapter in the book. Although I think, if I remember correctly, Gaussian elimination isn't even mentioned in the book. Good. Yeah, but Gaussian elimination is important, and it is also important not only to solve linear equation system, but because we can also use it to calculate the inverse of a matrix. I will not do this here because it's pretty straightforward, just application of the rules like I did it before. But it is important, which is why you will have an exercise about this in the tutorials. Good. So for the rest of today, I will focus on something that is related to matrices, which is the so-called determinants. Determinants are defined for square matrices, and the determinant of an n cross n matrix is defined as the signed volume spent by the column vectors. That is pretty straightforward if we look at it in 2D. In 2D, we have a 2 cross 2 matrix, so we can interpret the matrix values as column vectors. So in this case, we have A1, and here we have A2. And if we draw this in a two-dimensional coordinate system, we have here, again, this vector A1 and the vector A2. And then we see those vectors span up a volume, which in 2D is a parallelogram. And this defines then our determinant, and the notation of a determinant. There are different notations for this. One is that we write just that in front of the matrix. Another one is that we write these lines here to the left and to the right of the matrix, or to the coefficients of the matrix. And this is like I mentioned at the beginning, the difference here. Be careful with the difference between a matrix and the determinant of a matrix. Becomes clear here by how you write the brackets or the lines in the case of the determinant. And like I said, in a 2D case, this is defined as the volume of the parallelogram, but it says here the signed volume. So what does that mean? What is the signed volume of something? Or what is, for example, a signed parallelogram? The point is that it depends on in which order you write the column vectors. If you write the column vectors like we did here, A1, A2, in a counterclockwise way, then you get a positive result. So positive if vectors, the column vectors, are in counterclockwise order. So if this here is the first and this is the second, that's counterclockwise, or negative otherwise. So in this case, the volume is positive. In this case, if we write A2 and then A1 first, A2 first and then A1, it is negative. And that when you calculate the matrix, you will also see that A1, A2 is minus A2, A1. not going to prove this now, but we will see later when we learn how to calculate the determinant why this is the case. And that, of course, explains how we can interpret what the sign of a volume is, what it means, assigned volume, because it changes the sign when you change the order of the column vectors. In case of 2D, like I said, we have a parallelogram that is spanned by these two vectors. In 3D, we have a so-called parallelepiped, which is just a three-dimensional version of a parallelogram. It's basically a box where each side of the box is a parallelogram. And of course, we can also generalize this to 4D because determinants are defined for n cross n matrices, so there is no restriction on a dimension. But of course, in graphics, we are mostly interested in 3D or in 2D here in the lecture, because 3D is harder to draw and harder to explain. And in a lot of situations, 3D is just a straightforward generalization of 2D, which is why I'm often using 2D examples here. Good. So we know now what a determinant is. But of course, we also need to know how do we calculate it. And there is one approach or different way. There are different ways to do this, and one of them, probably the most common or popular one, is the so-called Laplace expansion, which sounds very complicated, but if you look at it and do it with an example, you see it's just a straightforward application of certain steps that you have to do, which is why we'll go to a detailed example now. But it sounds very, a little complex at the beginning, I guess, but it is really just straightforward. The Laplace expansion, when we do a Laplace expansion, we can calculate the determinant of a matrix as the sum of the products of the element of any row or column of the matrix with their cofactor. So we see we have a new term here, a cofactor. So we have to see what a cofactor is, and that is, of course, the part that is really annoying or sounds really complicated or confusing at first, but it is straightforward. Like I said, a cofactor is an entry Aij in an n cross n matrix A. Is the determinant of an n minus 1 cross n minus 1 matrix A dash that is obtained from A by removing the eth row and the jth column multiplied by minus 1 to the power of I plus j. So I guess you agree that this sounds very confusing, but let's go through an example and we'll see how straightforward this is. So you see a cofactor is related to an entry, to a coefficient of the matrix. So we calculate a cofactor. We can calculate a cofactor for each individual coefficient. So let's look in an example. We have this matrix here. Let's look at a cofactor 1, 3, which means so Aij is 1, 3. So that means we look at the first row and the third column, which means we look at this value here. And now if we look here, the cofactor of an n cross n matrix A is the determinant of the n minus 1 cross n minus 1 matrix A dash. So we see here, this is how we calculate, and this is why it's called expansion, because it is a recursive method. So we again need to calculate the determinant to get the cofactor, but it's a determinant with one dimension less. So if we do this recursively, in the end we end up with having a determinant with just a dimension of 1, and then the determinant is exactly the value of the coefficient. So we can recursively calculate that. So we have to get a matrix that has one dimension less, and we get this by removing the eth row and the jth column, which in our example is, of course, row 1 and column 3. And that means this remaining part here is now our matrix A dash, which has obviously one dimension less than the previous one. And then we multiply this with minus 1 to the power of the sum of these two coefficients, which in this case are minus 1 to the power of 1 plus 3, which is plus 1, which is why it was actually not written here on the slide. But I wrote it down now for illustration because it's plus 1, so it doesn't change. So this is just the sign of the determinant. And this is now, so we get another matrix where we have to get the determinant. And if we do this, then we get our cofactor here. And you see here the notation for cofactors is usually that we write a 1, 3 and then a C at the top. And then what we do is when we have these cofactors, we use we take them all, multiply them with the original coefficient, and then we sum them up. So what we do here, for example, here we have our coefficient A13 multiplied with the cofactor that we just calculated. Then we do this for the other coefficients, and then we sum them up, and then we have our determinant. Now the other coefficients, you see, we only take the first row here, because it says here in the procedure, we take the elements of any row or column of the matrix, so we don't have to calculate the cofactors for all values in the matrix, for all coefficients in the matrix, but just for one row or one column. And it doesn't matter which one we take, we can take any of them, which of course means I just took the first one here because we have the general case. If we have a matrix, then it's of course and we do it on paper, then it's of course very convenient or very reasonable to take the line or the row with the most zeros in there, because that saves you calculation time, because you always multiply with the cofactor, and if it's 0 then you don't have to you multiply with the coefficient, and when it's 0 then you don't have to calculate the cofactor. Good, so let's look at a quick example. We have here a 3x3 matrix. We want to get the determinant. So what we do in the first step, we decide which row or column we take. So here we have a 0, so let's take the first row, this here, and that means these here give this is A11, this is A12, and this is A13. So we get our coefficients here, and then we multiply them with the cofactor of the related submatrix, which, for example, in the first case, we cross out these here. So this is our matrix A dash, which we see also is here. But unfortunately, we don't even have to calculate that, because this is 0. So you see, this will end up to 0. And but if we look at the second one, we see, of course, we have to recursively now calculate the determinant of that matrix. So let's again take, for example, the first row, although we could pick any, and in this case it doesn't really matter. Then we write down again the coefficients here, and we multiply them with the matrix, the reduced matrix, which in that case for the first coefficient it's just 8. So we have here a new matrix, so we have to get the determinant, but since we just have one value, we're at the bottom of our recursion, so we just get the coefficient as the determinant. So what we end up here with after this step is we just have scalar values that we just need to multiply and sum up. But when doing the multiplication and the summation, of course we have to consider this other factor here, which is the -1 to the power of the sum of the indices, which for example, if you look at it here, you have A11, so 1 to the power of 2 is +1, so this is positive. Here we have 1, 2. 1 to the power of 1 plus 2 is 1 to the power of 3, -1 to the power of 3, that's -1, which is why we have a minus here. And here we have 1 to the power of 4, -1 to the power of 4, which is why we have a plus here. Similar here for the reduced matrices, and if you do that, you'll see that it adds up to 0. So this is the determinant of A is 0. Good. So you see here, it sounds very complicated, but it's just a straightforward procedure that you have to learn and go through. And yeah, fortunately, there is also an easier way to do this if we are just dealing with 3x3 or 2x3 matrices. If we have a 3x3 matrix, if you write it down in a general way, like I did it here with just letters A, B, C, and so on, then of course you can write down a general way, and then if you do that, and if you group the ones that have a positive factor and the one that have a negative factor, you end up getting this this formula here, which by the way is a good exercise to do that. And of course now you could just try to learn and remember that formula, but there is also a good trick to remember that, or to do it on paper, which is called the rule of Sarus, I think it's pronounced. It's a French mathematician. I don't speak French, but I think it's Sarus. And how you do that is just you write down the matrix a second time next to it, and then you just cross out the diagonals and write them down here, A, E, I, and here B, F, G, and here C, D, H. And then you see these are exactly here the positive values here. And then you cross out the diagonals in the other direction. Let's do it that way. That works. And then you see these are exactly the coefficients that you hear on the negative side. So this here is positive, these here are negative, and then you can just write them down. And that's of course a very easy way to remember it, and also to do the calculations when you're asked to do this in tutorials or exams, for example. Good, and it also works for the 2D case. You just take here the plus and here the minus, and then you have your 2D, your determinant of a 2x2 matrix. Unfortunately, it doesn't generalize to higher dimensions. So if we want to calculate with higher dimensions, of course, in graphics we often look at 3D spaces, but we are dealing with higher dimensional matrices in graphics. And if you want to do that, then of course you cannot use that. You have to use the Laplace expansion for that. Good. Related to the 3x3 matrix, just another example which is the same as before. Just I used different letters here. Instead of A, B, C, I used X, Y, Z, and V and W with an index for the second and third row. And then if you do again the Larousse thing, you can write it down. But if you choose the letters like this, you can also write them down in a different way. So you see here, if you do the positive thing and the negative thing, the negative direction, you will always end up having x times something positive minus x times something. And if you group that, then that the x, y, and z values are together, you end up with what I wrote here at the bottom. Now, of course, I have chosen these letters for a reason, and you probably already remember or can imagine how they look like. If you interpret this as a vector p of a random point, and this as a vector v, and this as a vector w, and you look carefully at this, I hope it starts looking familiar, because this is actually the scalar product of these two vectors v and w with a random point, the cross product of these two vectors v and w with a random point p. And yeah, so this is, I don't know the English word for it, but I think in Dutch it's called Eselsbrück. So if you have problems remembering the cross product, that's an easy way to do it. Good. So yeah, so now we know a lot about determinants. We know how to calculate them, but of course the question is always why do we use that? Why do we need them in the first place? Especially in relation to graphics, and the answer is similar to the matrices. We can use them to calculate important things. For example, we can use them to solve linear equation systems, and we can use them to calculate the inverse of a matrix. So let's look at a linear equation system first. We saw that we can solve them with Gaussian elimination, but we can also solve them by using the determinants with something that is called Cramer's rule, which is defined as we have a linear equation system. You remember we can write this with matrix notations in notation ax equals b, and then Cramer's rule said that the solution of the xi, so that's actually a little confusing notation here. So here let's just set x, y, and z to x1, x2, x3. Should correct that for next year on the slides. Yeah, sorry for that. So so then we can see Cramer's rule tells us that each xi can be calculated by dividing the determinant of two matrices. The second one is the original matrix that we get from the linear equation system. And the first one is a matrix A with I index at the top here, and that is obtained by replacing the ith column with this vector B here. So if we look at an example, here we have our matrix I, here we have our vector B, and here at the bottom we have the determinant of A. So this is always the matrix A. But at the top here we see here that here the first, the second, and the third column are different than in the matrix A. But these are exactly our vectors B. So this is A1, this is A2, and this is A3. So we just have to calculate the determinant of them, then divide it by each other, and then we get our solution x, y, and z, or x1, x2, and x3. And so the interesting question is, of course, why is that the case? And I will only show this for the two-dimensional case, where we have a 2 cross 2 matrix. And we said that we can interpret this then a linear equation system as each equation represents a line and the solution represents the intersection of the two lines. But if we have two lines and if they are not parallel, if they are linearly independent, then we also learned at the beginning that they can be used, that they define a 2D space with the base vectors being the vectors that we use to the direction vectors of the lines, which means we can also interpret this linear equation system as a linear combination in that coordinate system. So we take A1 as one base vector. So this is our A1 vector. We take A2 as the second base vector. And then the vector B is just a linear combination of these two vectors with the two factors x1 and x2. So if this is our vector B, then we have here the x-coordinate of this vector is x1 times a1, and the y-coordinate of that vector is x2 times a2. So this is just a different geometric interpretation of it, that we see it as a linear combination now of these two base vectors. And now if you remember that in 2D the determinant was defined as the signed volume of a parallelogram defined by these two base vectors, or defined by two base vectors in general, then if we look at, for example, the parallelogram that is defined by this vector A2 and this vector here, which is x1, a1, so this parallelogram here, that is then what we have here on the left side, the determinant of this matrix. That is the signed volume of this parallelogram. Now we know from geometry that if we shear a parallelogram, that is, if we just shift one side, the volume of the parallelogram doesn't change. So for example, if we take the right side here and move it up, so we get this parallelogram here, the volume of the parallelogram doesn't change. And that should be intuitively clear from the image, because you see if you shift it up, what you basically do is you cut off this part and then you add this part at the top, which means that the overall volume doesn't really change. The absolute value of the volume doesn't change by just shifting it up. Now if we look how this parallelogram is defined, it's defined by the vector B and the vector A2. So we can calculate the volume by getting the determinant of the matrix defined by these two column vectors. Now another thing we know from geometry is that scaling the side of a parallelogram with a scalar, scaling one side of the parallelogram changes the volume by the same factor. So for example, if you double the side of one if you double one side of the parallelogram, you also double its volume. And that means we can take this scalar value and write it in front of the determinant. And then we get the same value here, because scaling, multiplying it with a scalar value only changes scales the volume with the same amount. So it's no difference if we first double the page, double the side, and then calculate the volume, or if we double the volume and then if we double the volume directly. So which is why we can write it in front of it. Now if you look at that, of course that we can also write as x1 is BA divided by this determinant. And that is exactly what we have with Cramer's rule, only for the first coordinate, but the second one works in a similar way. We just have to take different vectors from the image. So you see here, this is a pretty good way to see this, how this works in 2D. That's actually, by the way, how the book starts. If you look at the chapter in the book, it starts with definition of determinants and this illustration here. And although if you really think about it based on the image, I think it's pretty straightforward, but I think you understand now why I decided to go the other way around and start with the introduction of matrices, because it's like more related to a generalization of the vector concept that we had before, and then do this at the end. But like I said, nevertheless, it's helpful to also read it in the book. Good. Another useful application of determinants, like I already said, is the calculation of inverse matrices. We can use determinants to calculate inverse matrices. Of course, we can, like I said, we can also use Gaussian elimination to calculate matrices, and similarly to Gaussian elimination and inverse matrices, I personally, if I do it on paper, I found Gaussian elimination more straightforward or simpler to do than the determinants, because that's always a lot of calculations that you have to write down. But of course, we don't want to do this in paper. We only do it in paper in the course because it is important for you to get an understanding of the theory behind it. But in practice, we want to implement it. And for example, if you have already implemented determinants, then using determinants to solve linear equation systems is much easier than implementing the Gaussian elimination. So you see that depending on the situation, one or another way makes more sense or is better to do, which is why it makes also sense to discuss different ways to do the very same thing, or to do the very same thing in with different approaches. And if we want to do it with inverse matrices, we have to introduce another matrix. So it's again a little confusing because there are a lot of new terminology here, but it's again pretty straightforward. What we do is we take a matrix and then divide each coefficient by the determinant of the matrix, and this matrix that we take, that is the adjoint of A, and that is the transpose of the cofactor matrix of A. And again, the cofactor matrix is the original matrix where we replace each coefficient with the cofactor. Sounds complicated, is pretty straightforward. We take the original matrix A, calculate for each entry the cofactor, then we replace this entry with its cofactor, and then we make the transpose of it, and that is then our matrix A. And because we already have the cofactors, we can easily calculate the determinant. Then we can divide each value in the adjoint matrix with this determinant, and then we have our inverse matrix. So it's a pretty straightforward way to do it. We just have to remember the procedure, but the actual thing is pretty straightforward, which is why I will not do it today. I think I bored you enough with endless calculations today. So, but this is, I think, a very good exercise for you. So I'm not sure if this is in the tutorials, but the Gaussian elimination to calculate inverse matrices, that is definitely in the tutorials. Good. Yeah, because it is in tutorials, because inverse matrices are very important for when we want to transform vectors with matrices, which is what we want to do next time. So, are there any questions? No? Then we close a little earlier today, and you have more times for the practicals.